Good morning, everyone. Thank you for coming to this morning's session on the last day of the Science Festival. Guess without further ado, I will introduce our speaker for the session today is Russell Arnott. Having been a punk rock guitarist and a school science teacher, he is now a marine scientist, educational consultant, and founder of Incredible Oceans CIC, which is a marine education non-profit organisation dedicated to teaching people about the importance of our ocean with a background in physical oceanography. I can't get my tongue around that. Russell's research looks at how plankton may change due to climate change. So over to you, Russell.
Cool. Thank you very much. Hello, everyone. So I'm gonna caveat this with the fact that I've never done this talk before. So good luck to all of you. I was really excited to come to the Orkneys. I've never been here before, but my uncle lived here for many years when I was growing up, so it's always had this kind of like, ooh, what goes on up there at the top of yeah of the world kind of thing. So when I chatted to Howie. And I was like, well, I could do this talk and do this. And it was a bit like, And then I said, and I've got this idea for a talk about superpowers of sea creatures. And I went, oh, yes. And I was like, oh, no, I need to do this talk. So here we go. Let's have a go at this. Sea creature superpowers. I quite like this image as well. I used Image Creator and AI. I spent ages typing in things like a plucky band of underwater superheroes, and it generated all kinds of absolute rubbish. But this was the best one. I thought it was quite good. There we go. Thank you, computers. Right, there we go. I thought I'd tell you a little bit about me. That this is me in two dimensions, much larger. That's my name, and this is one of my laboratories. So one of the things that frustrates me about science is where you have unnecessarily complicated words for really simple things. These tanks in the background are supposed to be called musicosms, making them sound they're just a big tank. And this is the top half of them, they're probably about the height of this theatre. And these are over in Sweden. And what I do is I fill them up with different plankton populations. And I can tweak the conditions inside and I can see how the plankton community responds. So this is what I ended up doing, which is quite good fun because I have a background in oceanography and oceanography, which is effectively the study of the water itself. And what I got frustrated with was if you're an oceanographer, you're like, I only care about the water. It's the water. I don't care about anything that lives in it or anything else. And I noticed quite early on that things were very, very siloed. And I found that frustrating. So I've kind of started looking about like, oh, physics and how does the physics of things affect the biology of things? So it's quite nice that this is kind of the idea behind this talk is to promote a little bit of multidisciplinarity and to show that, these very strict silos of chemistry, physics, biology, actually, fun things happen on those interfaces between different things. So I thought I'd show you just some nice pictures of oceanography stuff. So I spend a lot of time on boats. Sometimes they're big boats, sometimes they're small, and we get really high-tech things like scaffolding poles and put those over the side of boats with different equipment on to measure that. Sometimes we lower things onto the seabed. This is a really cool piece of equipment that fires sound up into the water, and it bounces off particles in the water. And from the Doppler shift, you can tell what direction the water's moving and how quickly. Sometimes we put floaty things in, and this is called a drogue buoy. It's got a big parachute on the bottom of it, and we have a GPS thing. And so this is up at Sellafield, and this was to make sure that nuclear power stations don't suck back in their hot coolant water, because then bad things tend to happen. And then sometimes I would pour pink dye in the water. This is called rhodamine, and it's quite safe, and I would pour it in. I had to wear this stuff because if I got any on my skin, it dyed my skin bright pink for 2 weeks. I did have an unfortunate accident with my foot once, and I had a pink foot for 2 weeks, which was good fun. So there we go. So we do things like that, and the pink dye we use to see like what the mixing potential of the water is and where a water parcel might go. I was also responsible for putting these things out. There's a big network of these wave buoys all around the UK, and they're quite big. They're about this kind of size, and this is what they look like when they go out brand new. They kind of bob up and down, and they've got accelerometers inside them. So all of you have an accelerometer in your pocket. It's basically a mobile phone, and it's how your phone knows whether it's that way up or that way up. So they've got the same things in those, and they can work out what direction the waves are coming from and how big. And that aerial on top, they send it to a computer on the shore, and so every 10 minutes you can just go on and see, oh, how big are the waves? And this has been really good for seeing. This network's been out for about 20 years now, and it's really useful for seeing actually are storms getting worse, more frequent, and helping councils inform, how much coastal protection that we need to put in place. So that's what they look like brand new. And then 6 months later, they get covered in algae and seaweed hangs off them and things. So it was my job to go around very glamorous and clean all the seaweed and stuff off them. And sometimes, when they were like this, boats hit them. And each one of these costs like £20,000. And so sometimes people are like, oh, I'll nick this. Or sometimes in storms, they break their moorings and go drifting. And so what we did is on Google Earth, we basically mapped where that dot in the middle is where we put like the weight so the buoy didn't move around. And so as the tide kind of moves backwards and forwards, it makes a circle. And then we can put a watch circle around it and it sends you a text message. And of course, it only ever sends you a text message when it breaks its mooring on like a Saturday night when you're down the pub with your friends and you're like, oh God, I have to go. And they just end up in random places. So this is one where I went straight from the office and it was like 4 miles from the nearest road and they weigh quarter of a ton. So I just was like, I don't know how I'm going to do this. So I just had to get down to my pants and just like drag this thing back into the sea so I could float it and then just walk for 4 miles in my pants through the sea, getting it back to the nearest road. So yeah, never a dull day. There we go. So these are the things which I've ended up studying, because I was like, oh, okay. And I approached this a little bit like an arrogant physicist at first, like, oh, the physics is the big thing, biology, who cares? And so I study these things, which are called phytoplankton. And so to give you an idea, they are single cell plants. So if you were to pull out one of your hairs and put that's what your hair looks like. And people are always like, what? My hair looks like a dead snake? I'm like, yeah, well, there we go. And so these are single cell plants that live in all of the water in the world. They live under ice, they live in ponds, puddles, lakes, streams, and all the world's ocean. And we call these phytoplankton. To break this down, phyto means something to do with plants, and plankton comes from the Greek word planktos, meaning to drift. So this literally means floating plants. And these are quite important. So what I'd like everyone to do is take a great big breath in, breathe that out. And that breath came from the trees. And that's what we're taught at school, that energy from the sun goes into the trees on land and they photosynthesize and pump out oxygen that keeps us alive. I'd like everyone to take a second breath. You breathe that one out. And that breath didn't come from the trees, that breath came from the seas. So basically, because the world's oceans cover almost three-quarters of our planet, and they're full of plankton, constantly absorbing carbon dioxide and sunlight and making oxygen. So even when you are in the middle of nowhere, miles from the coast, we've still got that link to the ocean where we're breathing in oxygen. And so when I do this talk in schools, I quite often say, so everyone, we're basically just breathing in plankton farts. And everyone's like, yes, breathing plankton farts. And that's the main thing that the schools remember when they go home and do talks. So there we go. So that's your new fact, younger audience members up there. There we go. So phytoplankton. So there we go. So they're also important because, again, like at school, when we think of food webs or food chains, there's always the one, and I remember the one at my school, it was like energy from the sun goes into grass, which goes into rabbits, and the rabbit is eaten by a fox. And you're like, oh, that's really boring. So we're going to do an ocean food chain where energy from the sun goes into phytoplankton, which goes into zooplankton, which goes into fish, yeah, which goes into humans. I typed in human. That's what came up in Google Images. There we go. So yeah, so basically, as well as giving us oxygen to keep us alive, also quite useful for giving us food from the ocean to keep us alive. So I'd like you all to join me now and to appreciate these tiny marvels, plankton, by saying thankton. There we go. So, without much ado, I will continue then. So I thought I've divided this into three different bits. We've got tiny physics, then we've got big physics, and then we've got deep physics. Okay, so we're going to start off with tiny physics. So I'm like, well, I've just talked to you about plankton. There's got to be some cool plankton physics going on. So I thought I'd talk a little bit about this eutrophication, a really big nerdy science word that basically means too many nutrients. And this is one of part of the research that I look at. And this is essentially where you've got too many nutrients going into our ocean. And this quite often is from agricultural runoff. If you put too much fertilizer on the fields, or you've got something like lots of cows, and each cow produces a ton of poop a year, that has to go somewhere. And quite often, all of this ends up in the ocean where it causes these giant plankton blooms. And so this is one of the Great Lakes, and you can see that green stuff up the top there. Have I got a laser? There we go. That is a plankton bloom that is so big you can see it from space. And these are problematic because, as well as like if you're a fish that needs to rely on your eyes to see, the water's really murky, you can't see stuff, but also blocks your gills. And the real danger comes is after the plankton bloom has happened, it then sinks and decomposes. And as it's rotting, it uses up the oxygen in the water and nothing can live there. So right now we've got about 500 oxygen dead zones around the world. So I'm trying to figure out some of the mechanisms that cause these algal blooms to happen. So yeah, this is a little bit about what they look like, and um, they're also quite bad for us. And so a lot of the work that I do is looking at how these happen in reservoirs, because if water companies spend a lot of money trying to stop these from happening. Because if you just suck a load of plankton into the water plant, it rips open the cells, and inside the cells, there's a chemical called josmin. I always feel like josmin sounds like a posh person's name. Yeah, my name's Josmin. There we go. Um, this is a chemical, and humans are insanely sensitive to this chemical. We are so sensitive, we can detect 1 nanogram in a liter of water. So our sensitivity to Josmin, everyone knows, like, oh yeah, sharks, you drop like a drop of water in a swimming pool and they can detect it. Our sensitivity to Josmin is better than sharks, if that makes sense. And so it doesn't take a lot for us to be like, "Ooh," and it makes our water taste all musty and smelly. And then we complain, and then the water companies get fined. So water companies spend a lot of money trying to stop this from happening. And incidentally, this is a good fact. Camels are also really sensitive to it, and it's that they use to find oases in the desert. That's a good fact, isn't it? There we go. Plankton helping camels. There we go. But some of these plankton blooms are quite nasty. And we call these red tides, and these are 200 species of plankton are actually toxic. And if you were to go swimming in this, you'd end up with like itchy arms and it would hurt your eyes and things like that. But the real danger is if this washes into a space where there's fish or shellfish and they absorb the plankton, then you can actually be in a situation where people have died from eating this toxin because it works its way up, it bioaccumulates through the food chain. So sometimes we call these harmful algal blooms, and unfortunately, because of climate change combined with this excess nutrients eutrophication, we're getting more of these. They're happening more often, and when they do happen, they happen with a higher severity. To give you an idea, in the UK, they cost the UK about 16 million pound a year to deal with, and this will be in like loss of earnings for tourism, as well as like having to try and deal with the cleanup and things. So they're a big problem. Um, so my research of what I'm trying to do, the physics behind this is, when it's like, has anyone here been on holiday somewhere really nice and warm? And you're like swimming in the sea, and you're like, oh, I like that. And it's nice and warm at the top, but then you put your hand down a little bit and it's freezing cold. You're like, oh, I don't like that. I'm just going to stay on the top bit. Well, plankton, if you're a type of plankton that's stuck at the bottom, you're like, that's not as much fun. I'm down in the cold bit. I'm not going to get as much light because I'm a plant. I need the light to grow. But if you're a plankton that can get into the top bit through the into the warm layer, you can really go crazy. And as a tiny plankton, going across that barrier is quite difficult. It's what we call the thermocline. It's a good word. And it's you trying to get through it. But if you can get up into that, then you can go crazy and you can bloom really quickly. And then you absorb the sunlight above it, and so the ones underneath don't do anything. So I'm trying to look at like, okay, so what happens if we mix the water and we break that barrier, or what do plankton cells do? How can they get up into that top bit? Do they swim up, or do they float up, and things like that? So that's part of the mechanisms and the physics that I'm looking at here. So a question I always get asked is, what's your favorite plankton? And thank you for asking. Right. So, my favorite plankton is Mesodynium rubrum. I love it so much. It is like, it's really cool. It is a harmful algal bloom species. It was first described by Darwin on board the Beagle. It was one of the first things to be looked at by Anton von Leeuwenhoek under a microscope. I was like, oh, this is brilliant. It's so amazing. So what it looks like, okay, from the top, if you look down on it, it looks like a sunflower. And because I was a physicist, I didn't know what this was. When I was looking at it under a microscope, I just called them sunflowers until an actual person who knew what they were talking about was like, "Oh yes, here we go." So they were just so in my head, they're still sunflowers. From the side, they're like two balls on top of each other, and the sunflower bits are like a ballerina's tutu around the middle. And what they do, these are just a single cell. I don't know if you can see, they've got these six bits coming off like that. So those are like tentacles, and they put those out like that to stop themselves from sinking, so they can stay in that top bit. So they're just like, yeah, yeah. And if something swims towards them, they can detect the movement from the pressure wave with their belt. So with their tutu, so they wrap the tentacles around the top half of them, and then they flap their tutu and they jump. And they hold the world record for being the biggest jumpers, jumping the furthest distance for their size. So they're about 50 microns, so the same thickness as a human hair, but they can jump 260 body lengths. So that's like us just being able to go "Hooah!" Up and like high five a passing aeroplane or something like that. So that, and when you're so small, swimming in water is like swimming in treacle or swimming in honey. So the fact that they're able to do this is brilliant. The other weird thing about them, and this is again arrogant physicists coming in my tanks, my mesocosms, I put filters on to stop zooplankton coming in because I wanted to look at how the plankton grow. And it's a little bit like trying to measure how grass grows if you've got a cow in the field. You're like, oh, it's not growing very well. So I wanted to get the cows out the field. I wanted to get rid of the zooplankton. What I didn't expect was the plants to eat each other. I'm like, what? Plants go. So this thing, when it's made, it doesn't have any ability to photosynthesize. So those bits at the bottom here, that's actually its mouth. And what it does, if something goes towards it, here we go, it eats other phytoplankton cells. Ready? Hom. Yes. And what it does, it dissolves it and steals the chloroplasts, the bits it needs to do photosynthesis. I was like, what? That's like us eating a lettuce, going a bit greener, and then being able to hang out in the sun and make our own sugar. Like I was like, this is an insane creature. There we go. Here's another picture of it. And this guy's like, he's not seen me. Oh, yes, I have. This is a plant eating another plant. I was like, this is mental. There we go. What is phytoplankton? Anyway, there we go. So I thought I'd show you this. We're going to move up into zooplankton now. The hydra. Hydra, named after the mythical beast in from ancient mythology. A multi-headed snake, and if you cut one of its arms off, then one of its heads off, two more grow back in its place. So this was one of the first things that Linnaeus named, who came up with the binomial naming system. So it's quite important. He was like, it's kind of like a hydra. It can regenerate its lost limbs. So if you do cut one off, it can grow one back. So clearly Linnaeus was aware of this, which is why he named it this. But it lives forever. You're like, what? I would just say this is a type of zooplankton that we get in like freshwater lakes. So they'll probably be in any freshwater lake or loch that we have around here. They reproduce asexually. So these are an animal that when they want to reproduce, they just kind of go and squeeze like another version of themselves out the side, and then it like drops off. I always say like it's a bit like if you were really bored and you just wanted someone to go down the pub with, you'd be like, and you could just produce a clone, and you're like, yay, let's go. It'd be a younger version of you, which would be weird. But there we go. So they're kind of cool. And these are actually, they sting, not us, thankfully, but they are related to corals and jellyfish. And so that's what this thing's doing here is it's stinging stuff. The other really cool thing about it is that people familiar with Wolverine. And so Wolverine in the Marvel movies, he's got these big skewers that come out between his knuckles and they rip and they cut him. And so when he puts them back in, he has to heal his skin. Well, hydras are a little bit like Wolverine because every time they eat, they don't have a mouth. So what they do is they literally rip a hole in themselves as their mouth stuff the food in, and then heal up again. And this is a picture, a video of them ripping their own skin open so they can then have a mouth. That is pretty mental. There we go. Go Hydras. So, uh, I was just like, what is this? So I thought I'd come on to this, the pistol shrimp. We're going a little bit bigger. And these are quite small. They're about 5 to 10 centimeters long. And these are absolutely incredible. You can see there, they've got this giant super claw. Super claw does absolutely amazing things. It's basically a little bit like a pistol. You can, hence the name, is you can, at top bit of the claw, they kind of bring it back and it locks in place and it's got a cavity underneath. And then when they find something, they can quickly close that claw in like a fraction of a second, and it causes what's something which is known as cavitation. So you can see it here kind of firing out there. And cavitation means it's basically causing such pressure it makes a load of bubbles. But then what happens, those bubbles collapse and amplify that wave, making it even more powerful. And so if you were to go down with a tiny microphone and put it like next to it, it would measure 190 decibels in sound. To give you an idea of decibels, like roadworks is about 130, something like that. So these are ridiculously loud, like a rocket taking off is 160 decibels. These are 190, this tiny thing, just whoosh. And they make these pressure waves. They just kind of come up to things like, oh, I want to attack you. It's just whoosh, making like a big fireball that goes out. And it's like cavitation is really powerful. Like, you get it. It's a problem if you get it around propellers because as the bubbles collapse, they cause extra kind of force, and you can actually get it dissolving propellers and things like that. So they're really, really amazing creatures. Here's an image, and you can see there that's the kind of top bit that kind of goes back a bit like locking a gun, and you can see that big hole at the bottom there. That as it slams down into it, it makes this cavitation, this pressure wave, which allows the pistol shrimp to kind of do its thing. Pretty amazing, I think so. So then we're going to go next. So we're going to go up to a nautilus, and nautilus is about this kind of size. I think they're really amazing nautiluses. People are always like, "Oh yeah, I know about squids, I know about octopuses, I know about cuttlefish." But nautiluses are kind of like the weird cousin. But people are like, "Oh, who is this?" So we're going to talk about and nautiluses. I just think are absolutely phenomenal. And they do loads of really cool physics. So first of all, we look at their eye. It's kind of a weird looking eye, but it's one of the simplest eyes on Earth. This is just a bony plate, right? And it's open to the water. So water goes through the slit and is actually like inside their eye. So it's like I just already think that's a really strange idea. But their eye works like a pinhole camera. It's that simple. So pinhole cameras, if people ever use one, if you see something like a fish, what happens? The light from the fish goes through that tiny hole, that aperture, and you get a picture upside down on the back of your retina, and then your brain switches it around the right way. So right now, all of us are actually seeing upside down, but our brain flips it round the other way, which is quite useful. Thank you, brain. Um, but yes, so I just love the fact that they've got this really, really simple eye. They're so primitive that they're like, yeah, this eye works. This is fine. They've also kind of famously, if you cut through the shell, they've got this beautiful logarithmic spiral inside. Quite often people are like, oh, the golden ratio. It's not the golden ratio. It is, in fact, a logarithmic spiral, to be a pedant. There we go. Well, what they do here, which is really cool, it's like, okay, if you want to move pull down in the water column, clearly they're a shell. It's like, how do you move up and down when you've got tentacles? So what they do, they work a little bit like a hot air balloon. So when they want to go up, they fill these chambers with air or remove it. And when they want to go down, they fill them with water. So they kind of work like a submarine or a hot air balloon, using that for buoyancy, which is pretty cool. So that's how they go up and down. And you can kind of see they normally have, I think they've cut through them, but they've normally got little valves in between each one of these chambers that allow them to do that. Um, but when it comes to moving side backwards and forwards, what they've got is this cool thing. It's sometimes called a siphon. The proper name for it, a good Scrabble word, is a hypernome. Ooh, that's a good word. It sounds like a hyperactive gnome. But a hypernome. And basically what they do is, I love the fact that they utilize Newton's third law, which is every action has an equal opposite reaction. So what they do is they suck water in and they blow it out. And as they blow the water out, they move backwards, which is quite cool. So that's how they move. I was like, oh my God, this is incredible. It's pretty cool. So yeah, I'm always impressed with Nautiluses. In case you're not impressed with Nautiluses enough, I'll show you how awesome they are. They evolved 500 million years ago, right? And they've barely changed. But not only have they not barely changed, they have survived five mass extinction events, which is pretty incredible. And now, after all that, they're now endangered because they've got nice shells. And it's like, how do you survive five mass extinction events, and then we come along and like, oh, you're pretty, and we end up wiping them out. So we need to sort out the protect the nautiluses. Yes, there we go. Um, so then I thought, and then when I go next up, we just talk about fish, and people are like, fish? Fish are just fish, aren't they? It's just, what do they do? Like, who cares about fish? Well, all fish have a superpower, which I'm like, oh, this is actually amazing. So if you look along side of a fish, there's something there called the lateral line, which literally means a line down the side. And this does lots and lots of really awesome things. It's slightly raised, and if you stroke a fish in one direction, like from head to tail, you won't feel it. But if you go from tail up to the head, you might feel it stick in your hands. Sometimes it's like raised. And this is basically a line of electrical sensors. And so what a fish can do, a bit like a mesodynium, is that it can detect pressure waves with this. So if something moves towards the fish, it can feel that movement on its side, sometimes before it sees it. It can also detect electrical signals, so it could detect things like movement inside something or a heartbeat. And so this helps the fish roll together. So instead of constantly having to kind of look at what fish are next to you, what they can do is just be like, oh, okay, I can kind of feel where my neighbor is. That's quite nice. And then they can move around. And then obviously things like sharks have taken this to the next kind of like super level. And if you look inside sharks' noses, they've got loads of like pits, a bit like blackheads, that are full of mucus. And these have a great name. These were called by after the Italian scientists that discovered these, and they're called ampullae. I can never say that. Ampullae of Lorenzini. And what they do, they're full of like a special kind of slime that can measure electrical potential. So the sharks could detect the difference between the top and the bottom. And so as they move their head around, they can measure all these different electrical fields. And so sharks, what they're trying to do is if something is injured and is like swimming badly and is panicking or has got some kind of like problem with its heart or something, they can feel the heartbeat. And so preferentially, they're going to go for sick and injured creatures or creatures that maybe have some kind of genetic birth defect. So sharks are actually really important, like neighbors, not neighbors, doctors of the ocean. And what they do is they come along, and if there is a sick animal, they will remove it from the food chain by eating it. They've been on Earth like for longer than trees have been. So sharks have an amazing immune system. And in the areas where we've removed the sharks, diseases and genetic problems kind of spread throughout the populations. So looking after our sharks also looks after our oceans. So that's another reason we need to do that. So I think we've got small. We've kind of finished the small bit. Oh no, we haven't finished the small torpedo fish. I can't believe we get these in British waters. These are like they're kind of like a ray, but what is amazing about them is they've got modified muscled cells on their wings, which we call electrocytes, and those electrocytes allow buildup of electricity inside them. And they can zap up to 200 volts. Like fishermen have been killed by handling these. That is how hardcore they are. I don't know why that's in the middle. It's in the middle. If you want to ask some questions, if any of that stuff I've just said sparks a question, it's there in the middle. There you go. I'm going to move on. So cool. Torpedo fish. I really like the Latin name. Torpedo, torpedo. There we go. That's a good one. Um, they have these electrocytes inside them, and it was this that inspired this person. Any idea who this is? Volta. It is Volta. Alessandro Volta. He's an Italian man. He did a lot of work around. I'll stop doing that. A lot of work around electricity, and crucially, what we've got down here is his thing, which is known as a voltaic pile. And this was the world's first battery. And you can make one of these at home. All Alessandro did is it's alternating stacks of copper and zinc discs piled up on top of each other with a bit of cloth dipped in salty water in between. And he made this first battery, and he was like, "It's kind of cool. I've made a battery. I can make electricity." Wow, okay. Oh, I've really been waffling for a long time. I apologize. I've got a 15-minute warning. Right, let's go on. Basically, the first ever battery was inspired by the torpedo fish. So let's go on to some whale physics. Yes, whale physics. I love it. So I thought we'd go big. I really love whales. I think they're awesome creatures. So I thought I'd celebrate some of these. So all whales descended from this thing, a weird hyena dog that was around in what modern day Pakistan about 15 million years ago. And so they were originally hairy and had like four legs. And over time, they they kind of lost a lot of their hair. They lost their back legs as they evolved. But they've still got some remnants of those today. And one of the things that they've got, basically the size of a modern day hyena, over millions of years as they evolved, they lost their back legs and they lost their hair, and then we kind of get the whale that we kind of know and love today. But they've still got these little remnants of different things. And one of the things that they've got, well, is they've still got the leftover bits of their hair. So we divide whales into toothed whales and basically hairy whales or whales with a big moustache inside their mouth. So this is baleen, and if you've seen Finding Nemo, this is where what Nemo gets tangled up in, and they use this to kind of eat. Um, but they've also got hair on the outside of them. And so these giant lumps are called tubercles, and these are actually the leftover parts of root hairs. And these have an amazing hydrodynamic effect that help humpback whales. So if you look at the humpback whale, its Latin name literally means big wing from New England. So which and they have got this giant arm here. It's such a big arm. To give you an idea, it's 2 humans long. Okay, that is the biggest arm on Earth. And so what they did, they were quite interested in the fact that it's kind of knobbly all the way along. So these are root hairs again, tubercles along the end. So what researchers did is they made like a normal wing and then they made one with knobbles on it, and they tested to see how it worked. And what they found out is that what those nodules do, something called the tubercle effect, and they actually funnel air along those grooves, which creates more lift, which makes the humpback whale more streamlined and more energy efficient and able to do better kind of movements because people were really impressed at how something so big could be so nimble. And this is one of the ways they do that. Um, Blue whales, largest animal that's ever lived on Earth, which is pretty incredible that we also exist on Earth at the same time as this. I think they're absolutely phenomenal creatures. But despite being the biggest animal, they eat one of the smallest things on Earth, krill. Uh, my favorite krill fact is if you got all of the humans on Earth, you put them on a set of scales, and you've got all the krill on Earth, you put that on a set of scales, the krill weighs 100 times more. There is a lot of krill in the ocean, and which is why we're able to sustain our whale populations. So this is what they look like, krill. They're tiny little kind of prawns on the end of your finger. Um, and what is amazing about these blue whales is when they feed, they open their mouth up and they swallow. So they weigh 100 tons and they swallow 100 tons of krill and water in their mouth. So when they open their mouth, they double in size and weight. And so opening their mouth at the right point is kind of important. If they open their mouth too soon, then they and they kind of break their jaws and it just kind of and it means the krill can escape. If they open it too late, they create a pressure wave which pushes the krill away. So they need to know exactly when to open their mouth. And I thought that was pretty incredible. 500,000 calories in a single gulp. I just thought I was on coal, and that was of a fin whale, which is the slightly smaller one. But I was like, God, I was there a week ago. There we go. I thought that's quite cool. So anyway, so what they've got in between on those bits, like on the archway up here, is they've got this organ that they discovered, which is kind of like a balloon between two oak trees. That's how it was kind of measured, and that allows whales to detect the pressure as they swim towards things. So they know basically the key moment to open their mouths, which I thought was pretty amazing. And if you look inside a whale's mouth, their tongue, right, weighs as much as an African elephant and can fit 2 football teams on it. which I was like, this is insane. So when they eat, what they do is they swallow all that, put it in their mouth, but they don't want to swallow the seawater. So they press their tongue up against the roof of their mouth. All the water sprays out through the sides there, and they swallow the krill down. So I always invite people to, when you're next having cereal, to have a go at eating like a whale and spray all the milk out between your teeth and swallow the Rice Krispies down. And you'll be like, oh, this is great. I'm at one with my ocean friends. There we go. Uh, Right, let's get rid of this. Right. But I thought I'd finish up with the toothed whales because I'm conscious I'm running out of time. The toothed whales, this is definitely my favorite sea creature. They are absolutely amazing sperm whale. To give you an idea of their size, this is how big the females are. The males are about 26 meters long, the largest carnivore on Earth, which is pretty cool. But they also hold the world record for being the loudest animal on Earth. So this is Steve Maxwell swimming next to them, and you've got to be really careful when you swim next to sperm whales because they're so loud they can actually knock you unconscious, which is insane. Because particles in water are much closer together, you can have much louder sounds underwater than you get in air. And so sperm whales are so loud, they're 230 decibels. That is how loud they've been uh, they've been recorded. In fact, they are so loud, sperm whales, that as well as being able to knock things unconscious and stun things, able to talk to each other anywhere on the planet. And how they do this is in oceanography, we've got something called the SOFAR channel, which is the sound fixing and ranging channels. And this is because as different densities of water happen, what it does is it focuses sound waves along a certain depth that's about 200 to 300 meters. And it works like a big kind of fiber optic cable, kind of bending those waves along this particular density gradient across the ocean. And so whales have known to kind of go to this and shout at each other across whole ocean basins. And something like a sperm whale or something like a humpback whale or a blue whale will be about 180, 190 decibels, but the sperm whale being 230 decibels means that in theory they can talk to each other anywhere on Earth. They see us with mobile phones and they're like, why don't you just shout to each other? There we go. So yeah, that I thought that's pretty cool. And how they make these massive noises is pretty incredible as well. So up here they've got their blowhole and their whole head, their brains up here, their head is filled with a special type of oil, which is called spermaceti, and that's what we used to hunt the whales for. And so what they do, this whole head is like a massive guitar amplifier. And what they do is they make a sound at their blowhole. It travels through, bounces off their forehead, and then blasts out the front there. And it's pretty incredible. I went to the National Museum of Scotland on my way up here, and they've got a sperm whale skull. You can see their forehead is like a giant radar dish, basically helping blast that sound out into the water. It's pretty incredible. Definitely go if you next time you're in Glasgow, check that out. And I was lucky enough to play around with some of this oil in the Azores this year because a whale washed up on the beach and they went and got some of it. And it was amazing because this is basically crystallized in here. And then I held it in my hands just for like, I don't know, a minute and it liquefied. And so this weird substance kind of operates and has all these amazing physical properties that allow sound to propagate through it. I was like, oh my God, I want to do all these really cool nerdy physics tests on it, but they wouldn't let me take it away. But there we go. But I thought that was kind of cool. And they 5 minutes. Okay. I think I definitely you can tell I've not done this talk before because I've massively overrun. I'm going to leave it there temporarily, 5 minutes left, because I feel like it would be nice to have some questions. But there we go. What I'm going to quickly do is look at this cool stuff about deep things and pressure and whales and poo and going into the ocean trenches, deep physics and how much pressure and imploding and blobfish. Oh, shall I finish with my blobfish fact really quickly? This everyone, okay, right, blobfish. Everyone's like, oh, look, it's really ugly, right? The reason they're ugly is at depth they look like this, and the reason they look ugly is they basically undergo massive depressurization, and so that is a fish that's basically turned inside out. It's a little bit like aliens taking us to like another planet and calling us melty faces because of the acidic atmosphere or something like that. So it's actually quite sad blobfish, isn't it? So yeah, that's actually what they look like, not blobby. There we go. Um, anyway, we'll continue. I will finish there with this is what I do. Incredible Oceans. Unbelievably, this is a statistic that 1 in 5 UK children have never seen the sea. This is why I set up Incredible Oceans to do talks I sometimes dress as a pirate. We do things and festivals and schools and conferences, all things like that. So let me know if you need any of those things. I have a book. All proceeds from the book go back into our community interest company to help us kind of continue that. I will be signing it. I've got lots of different color pens and I can draw a picture of your favorite sea creature in it. There we go. And I will finish up there with some questions. Thank you very much. Cool. Make
Thank
my talk
you.
shorter.
That was absolutely fantastic. I didn't want to stop you, but unfortunately, we do have another presentation coming in after you. So definitely fill in your feedback forms and we'll get Russ back next year again. But no, thank you so much. Your passion and excitement for the subject really, I think it's infected everybody here. But
I needed to nerd out less about plankton at the beginning. You could tell I was really into my plankton.
well,
Yeah.
sunflower plankton, I
Mm.
mean, to start with. So, does anyone have any questions in the room? We've got one right in the middle here, but we've got one here just now. So, is geosym why Jossum, sorry, why water bottles stored damp taste fusty?
Ooh, I guess so, because Josmin, if there was any kind of plankton cells that got in there and the plankton cells died, then yes, that kind of mustiness might do that. But yeah, now I guess part of it as well is the water that we get out our taps has got lots of other things added to it to make it clean, fluorine and bits of chlorine and things yeah, that stuff is so I guess that kind of undergoes chemical processes and breaks down as well as like bits of the water bottle itself going in. One of my plankton, this is one of the things I learnt. I have a plankton machine where I pour my plankton, and every time it cuts a laser, it takes a photograph. The person showing me how to use this machine said, "Do you ever put bottled water through it?" And I went, "No." And we went to the supermarket, got bottled water, and in every milliliter, there were 30,000 plastic ribbons. And so now I'm like, drink plastic water anymore? There we go. Anyway,
Wow. Yep,
enjoy that
it's
fact. There we go.
terrifying.
Yeah.
Indeed.
Oh, yeah, wonderful talk. Great wordplay. I was wondering about the shape of the plankton,
Mhm.
because in your opening slide, they looked like planks. They were like spear. And
Yeah.
I always thought of planktons as being round or a single cell. When you use the term single celled, I would
Mm.
thought like an amoeba or something, but plankton is the essential shape of the plankton like the.
Well, this is, well, happens to be the morphology of plankton is my expertise. I can read you my PhD dissertation,
All right.
but basically, plankton. One of the reasons I do what I do is when you model plankton, you assume that they're all balls because in theory, a sphere is the perfect surface area to volume ratio. So in terms of trying to do chemical exchanges and things with the water, get rid of things and absorb stuff, you'd think on paper, all plankton should be spheres, but they all come in all kinds of weird and wonderful sizes and shapes. And they can also change their shape depending on their environment. So there was one really cool piece of research. There was this plankton that was like a spiky ball, and the spikes were there similarly to stop it from sinking. So it had these spikes on it to increase its drag. So then what they did is they put it in a container and they blasted it with loads and loads of turbulence. And it was like, oh god. And then it realized what it was trying to do was to sink out of what it thought was like a wavy area. So it could sink deeper down to get away from the waves. So to enable it to sink, each subsequent generation of this plankton cell grew shorter and shorter and shorter spikes until it was almost like a ball to allow it to sink. Then they turned the turbulence off, and then each subsequent generation grew its spines back. So they're really adaptable and have all kinds of weird shapes. But yeah, I can talk to the hydrodynamics as well of plankton cells because hydrodynamics does weird stuff at a small scale because water is so viscous. So you don't need to be streamlined, really, but it depends on your sinking rate and size and the environment that you want to live in and things. I could go on forever about plankton shape.
Oh yeah.
So,
Well,
so
like you could go on forever about the nature of a point.
yeah.
Right. Thanks.
Any other questions in the room? Oh, right at the back. So we've got one here. It's how much bigger does the human population have to get to level the weighing scales with the krill?
Oh, that's a good. I could do the maths, but not in my head. We'd need well, what is 100 times? So I actually don't know how much whole human waste weighs. So I'll figure that out. That's a good question. I'll figure that out. I don't know
We'll,
off
we'll
the top
get
of
a
my
flip
head. It
chart
needs
for
to get,
after.
yeah, we'll see if we ever overtake krill. That would be interesting. Yeah.
Yes, I was interested in the ocean, where sorry, the oxygen depleted zones
Hmm.
in the ocean, and you were saying that that is because of, in effect, a lot of runoff nutrients from land that
Yeah.
cause these blooms to occur. Has any work been done on mitigating those and, taking the nutrients out? I mean,
That,
one thing I thought of is perhaps you could just harvest seaweed and stop it recycling so that you can pull it out and we can use
mm.
the seaweed for lots of things.
But I think part of it is to I think quite often marine conservation and it's or conservationists in general are pitched against farmers, and I feel like it's very easy to tag farmers with like, oh, all you do is damage the environment. Like trying to produce as much food as they can for us is really, really important. So I think part of it is about trying to work with farmers to help encourage more sustainable farming practices. One of the things I think it's quite useful is seaweed. Seaweed is really good at absorbing excess nutrients as well as providing a nursery ground. And weirdly, by feeding seaweed to cows, you can also reduce the amount of methane that they produce. So it's been nice. I've been talking to some seaweed farms that are working with the National Farmers Union and things like that to try and kind of work together. Another part of it is kind of reducing the amount of sewage that we pump out into our water, because obviously that's also nutrients for phytoplankton. But yeah, trying to mitigate this is kind of a crucial thing. I think partly, we've got 1 billion cows on the planet, and each one produces a ton of manure a year, and that needs to go somewhere. And quite often especially these big kind of factory farms, that does end up being agricultural slurry, which works its way into our ocean. So yeah, in terms of trying to sort things out, yeah, it's basically we need to sort out our water quality and adopt more sustainable agricultural practices, or use that manure in a more effective way, like biogas generation and things. So, mm.
Okay. Any other questions down the front here? One more here. What's the approximate plankton count in a litre of seawater?
Oh, that's a good question. It depends on the plankton density and where you are. I mean, in my tanks, I probably was measuring. I could measure, I don't know, probably about 6,000 cells in about 10 milliliters. That wasn't like, but if it was like, yeah, so you get a lot in not very much space. So yeah, but when it's like pea soup kind of color, like those harmful algal blooms, yeah, you'll get hundreds of thousands of cells in a very small volume. But yeah, so okay.
I was just thinking, given that along the lateral line of a fish,
Mm,
they're sensitive to electric fields and the sharks are sensitive to electric fields, the impact of undersea electrical cables,
mm.
the huge transfer cables that are being laid currently.
Yeah, I mean, I'm not sure. I don't know of any research that's being done on it per se, but you definitely, one of the things that people are like when you go shark diving and you go in the metal cage, quite often when you see those videos of the sharks coming really close up and getting in with the cage, part of it isn't because they're like, oh yeah, I want to eat the diver. They're a bit like, whoa, this is a lot of this weird metal substance, and they're just trying to like figure it out, and they're getting some peculiar readings. But quite often you see when you are around these larger sharks, they will interact with metal objects and things with electrical currents in differently. So I probably that is the case. And there is a company in Australia called Shark Bands, and they basically make the wristbands that give off really strong magnetic fields. So the idea is that surfers can wear them. And so if a shark does go swims towards them, then they're like, it's kind of like a really like loud noise effectively, but electrical loud noise that will deter the shark. So yeah, it'd be interesting to know if things like wind turbines and undersea power cables and things are having what effects they have on them. My understanding is that they're generally quite localized, so I don't think they would be interfering with like migration patterns and things like that and behavior unless the shark was like really, really close to it. So,
can help you with that one actually.
Oh, really?
So I work in the offshore renewable energy sector, and actually it was a big problem when we first laid the first transatlantic telephone wires from UK to America. The sharks kept biting through the cables because of the electromagnetic field. So that's why they've been developed over the last nearly 100 years to have layers of armor around the cables to reduce the radiation into the water, to stop attracting the sharks,
That's
but also to
fascinating.
stop them being bitten through as well. So yeah, we've had about 100 years of development to try and make sure that we're not disrupting the sharks.
Right. If
Plus, they're
only,
buried as well, so they're buried on average about 3 to 8 meters deep, depending on the type of the seabed they're in as well.
thank you. And if only there was a talk about submarine cables today in the science festival. There we go.
Any other questions in the room or on Slido? We can still take questions as well.
You, you, you have to tell me when to stop. So I'm just like,
Oh,
oh, this is
you,
great
I
fun.
mean, you stopped early after I gave you a 5 minute warning, so you've still got another
Oh,
7 minutes if you want.
oh, okay. Oh, that's good. I could quickly do some other slides. No,
I'll cheerfully not ask a question if we get to see some more of your other slides.
I, I, I could quickly do some. I didn't realize that was what the 5 minutes meant. I thought it was 5 minutes, and then like we have to get out. I was like, ah,
Can I sneak a quick one in?
Yeah.
yeah.
Just to know, are there any synthetic or mineral oils that have the same sound conductivity properties as spermaceti? And are there actually any applications today for amplifying sound transmission using oil of any description?
That's a really good idea. Really amazing question. So, from what I gather, is the spermaceti oil is a really, really complicated mixture of different esters. And it was interesting because someone else that I was out with used to be an analytical chemist, and she was also fascinated by spermaceti oil. We were trying to figure out. So, one of the other kind of really cool things that it does, as well as acting as a sound amplifier, it's that helps the sperm whales dive into the deep ocean. So we're used to thinking of whales as surface creatures, but sperm whales are actually deep sea creatures that happen to just come up to the surface to breathe and then go back down. So in every hour, they'll spend 50 minutes of it in the deep ocean, about 2,000 meters. So if they had to swim down that whole time, by the time they got there, they would have used up quite a lot of their oxygen. So what they do is that spermaceti oil, they actually there's got a big muscle around the edge of it, and they remove the blood from the muscle, which then exposes the oil to the colder temperature of the ocean. The oil then kind of like semi-solidifies and becomes much denser, and the whale is dragged underwater by its nose, which is again phenomenal to have like an oily, waxy substance that can operate at those things, but also because you still need it in the deep ocean to not be affected by pressure, so they can still see and echolocate and stun giant squids and things deep underwater. So it is an actual amazing substance. And I think one of my favorite facts about it is it stays liquid and still lubricates things at really, really like low temperatures, so low that NASA used spermaceti oil to lubricate all their space probes up until like the mid 80s because they couldn't find a decent man-made alternative. And so it's quite nice if you think about like the Voyager space probe, which left our solar system 10 years ago. And on board that, you've got pictures of sperm whales, and you've got on the golden records, they've got sound of whale song, but the only DNA is on that space probe is actually whale oil and sperm whale DNA that's been taken out of our solar system. So that's quite cool as well. But yeah, in terms of the acoustic properties, there's whole papers where they look at the different pressure, temperature combinations and look at how different frequencies of sound pass through it at different speeds. So you can get really nerdy around spermaceti, which I did for a little bit. There we go. But yeah, there you go.
Okay, we've got 2 minutes for one more creature or one more question.
We do one more creature. Okay. Well, I feel like we're on the Mariana snailfish, so I thought I'd just do this. So I thought it was really interesting that as you go down into the Mariana Trench, I've got quite a nice animation. Let's quickly do this. There we go. La la la. I was playing around with animations. Let's do an animation. Here we go. So let's go down into the depth, really deep, down into the Mariana Trench. This at the bottom of the Mariana Trench, so deep, it's almost 11 kilometers deep. It's insanely deep, and the reason it's so difficult to get down there is because of the pressure. So if you think that so we're going to pretend we're in fresh water. So we've got a box of water, of fresh water. The box itself doesn't weigh anything. We're just weighing the water inside it. That weighs a ton. And then you realize, okay, so then if I stood at the bottom of the Mariana Trench, I've got 11,000 of these boxes above me going up, pressing down. And so this is what causes the pressure. So if I got at that point, every single square centimeter on my skin has got the equivalent of an adult male walrus pressing down on it. And so what that means is if I was at the bottom of the Mariana Trench and my submarine got a hole in it, the water would spray in with so much pressure that if I put my hand through it, it would cut my hand off like a laser. Which is pretty incredible. And so this is with the Ocean Gate. Everyone was like, "Oh, what a poor way for those millionaires to die." Actually, the best way ever, because they were looking at the Titanic, and the next thing they imploded. And at that pressure, they were only about 4,000 meters. Even at that pressure, which isn't even half the Mariana Trench, they would have been turned into a cloud of like atoms by the pressure in less than a second. And they were just a cloud of bits of human, which is incredible. Even it's pretty phenomenal. So and to show you like pressure, okay. So old deep sea divers, in order to kind of help them breathe, you had a pump at the top, and sometimes this was motorized, sometimes this was hand pumped. And people was like, "Oh, you've got to make sure that they get the air, otherwise they die." But what would happen if the pump broke more often than them suffocating is that pump allowed a link to the surface and actually equalized the pressure. And what would happen if the pump broke is all of a sudden that water pressure would force the entire diver's body up into the helmet. And they myth busted this with an actual deep sea diver thing, and they used like a side skeleton covered in like pig flesh. And you can see, I think this was only 100 meters underwater, and only 100 meters, that was enough to cause that implosion. So it's pretty incredible pressure and what it does. And so what's interesting is that below about 8,000 meters, you can't get bones anymore because the geochemistry causes bones to dissolve. So the deepest bony fish that we've got is this thing called the Mariana snailfish. And so when you look at, okay, so what is happening inside the cells of the Mariana snailfish that can allow it to exist at that depth? We've got this chemical called trimethylamine nitrous oxide, and that is the we've all smelt it. That is the chemical that is responsible for fishy smell. And as a fish rots, it gives off a nasty smell. But what is quite cool is if you plot, where we're getting nerdy on a graph here, if you plot the amount that's of trimethylamine oxide there versus depth, you can see that as you get deeper, the fish get fishier because it's that chemical that allows the cells to withstand the pressure. How cool is that? That's a pretty cool fact. There we go. And I like to end with a nerdy graph because we are at a science festival, aren't we? There we go.
Thank you for
Mhm.
ending on that and not the
Yeah,
imploding humans.
yeah, yeah. So, yeah. If you want, I'll be in that roomy thing there. If people want to come say hi, buy a
Yes.
book. I've only got 12 of them. So if you want one, they make great Christmas presents. Yeah.
But thank you again. And yes, if you want to see Russell back here again next year, please do leave us feedback either digitally through the QR code or on the hard copies of the forms around. It also helps Science Festival with our funding so that we can continue to bring fantastic speakers like Russell to Orkney to talk to you about the weird and wonderful creatures in the sea. This year, we also have a prize where if you send us your feedback, you will be entered into prize draw for the chance to win £100 of Northlink ferry vouchers. Festival attendees also can claim a 10% discount in the Orkney Distillery shop or cafe. Just wave your ticket when you go in and you can get a 10% discount. The next event in here at the Phoenix is Dr. Catherine Vaughan's, who'll be telling us about recycling ocean plastic at 11:30. We hope you've enjoyed the festival and continue to enjoy the festival for the rest of the day, and hope to see you again next year. But thank you once again so much, Russell. That was absolutely fantastic.